Okay, today we're going to learn about a method of differentiation called implicit differentiation. If you think of what the word implicit means, it means kind of subtle, not straightforward. Very straightforward would be explicit, not straightforward would be implicit. And so you'll see why that was maybe a good choice of words as we go. So let's first begin with this equation right here. It's an equation involving x's and y's. If we were to graph it, we would find all the points on the xy plane that make that statement true. Notice that 1, 2 is one place where it's true. Put in 1 for x and 2 for y, you get a 10 out. So suppose we're interested in what's the slope of the graph of this function at the point 1, 2. Say we wanted the tangent line, the tangent line at the point 1, 2. How would we find it? Well, one way is to first solve it for y, and let's go ahead and do it. So if I solve it for y, I'm going to first factor a y out of these terms, and then bring this over to the other side, and then we can write it like this. I always like to have a negative enclosed between things rather than out in the open. If it's out in the open, it's easy to get lost, or maybe if you have a sloppy equal sign, you think it's part of the equal sign. It's just a little bit safer to have it rolled in there in between them. So anyway, there's that, and now I'm going to take the derivative. And recall the quotient rule says you take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Okay, there it is, and we want the derivative at when x is equal to 1. You can write it like that. And when x is equal to 1, you're going to get 3 plus 1 is 4. 4 times 2 is going to be negative 8. This is going to be 10 minus 2 is 8, times 3 is 24, minus 24. And the bottom, you're going to get 3 plus 1 is 4. 4 squared is 16. So you get negative 32 over 16, which is negative 2. So there's the slope of the tangent line. If you actually wanted the tangent line, remember that the equation of a line which goes through the point AB with slope m is given by this. And so in our case, we would have y minus 2 is equal to the slope times x minus 1. And solve that for y, and you got it. Okay, so that's one way to do it. But here's another way to do it. Okay, suppose you had this equation. And you wanted to take the derivative of this equation, which means if this function is equal to this function, then the derivative of this side is going to be equal to the derivative of this side, because if the functions are the same, then their slopes are going to be the same at every point. So, so you take the derivative of both sides, and let's go ahead and do it. Let's see, here we have to use the product rule. So the derivative of this is 3 times, leave that one alone, plus 3x times the derivative of this one. Here the derivative of 2x is 2, and again the derivative of sine is cosine of x. Derivative of 10 is 0. So there you go. So now we're going to do the same sort of thing, but now we're just going to acknowledge the fact that even though we don't know explicitly what it is, that this y is indeed a function of x. We're thinking of it as always as a function of x. X is your variable, y is the function. So you have this plus 2x plus y of x is equal to 10. So we do exactly the same thing we did here. Here we're going to have to use the product rule. The derivative of the first is 3. Then you have the y, you leave that alone. I'm just going to write it without the y of x just to save a little bother. So the derivative of the first times the second plus the first times the derivative of the second. Well, the derivative of y is dy dx. That's what the derivative of y is. 2x, same as always. The derivative of that is 2. And then again we have the derivative of this thing, which is dy dx, and that's equal to 0. So same thing we did here. This was a function of x, and so we took its derivative. This is just a regular x, so the derivative of 2x is just 2. Okay, same thing here. Every place we had a cosine of x here, we have a dy dx here. Same idea. Okay, so now I want to solve this for dy dx. Let's see once if I can do it just a couple steps. I'm going to factor a dy dx out of both of these terms, and I'm going to be left with a 3x plus 1. I'm going to bring these over to the other side. And then, just because I'm short on room here, I'm going to divide both sides by the 3x plus 1. Like so. And so that's the derivative at any point, and I want it at the point where x is equal to 1 and y is equal to 2. So what's that going to be equal to? Well, let me make another line for that. So dy dx at the point 1, 2 is equal to, it's going to be negative 6 minus 2 is going to be a negative 8 on top, and it's going to be 3 plus 1 is 4 on the bottom. We get negative 2 again, same slope we had before, as we had to have had happen. So there it is. And then you can get your line, same as we did before. So this is called implicit differentiation. So, so you can kind of see where this particular problem, you could have done it either way. This way is maybe just a little bit easier, but you know, they're both fine. However, you can have other equations like this one, where it's impossible to solve it for y. Okay, I encourage you, go ahead to Decimus. Remember what Decimus is. Go to Decimus and graph this out. Just put in x plus y plus x cubed plus y cubed plus x to the fourth y to the fourth is equal to 28. The point 1, 2 is also on this graph, because if you stick 1, 2 in here, you get 28. But this is a weird looking thing. In fact, it's not even a function. Okay, it's not even a function. But it does go through the point 1, 2. And if we're still interested in the slope of this thing, say we want the tangent line at the point 1, 2, how would we go about getting it? Here we have no choice but to use implicit differentiation. So let's go ahead and do it. Okay? So, let's see, what do we get here? I'll start right here. I'll take the derivative of everything. And again, let me just clarify here, just for, I've taught this enough that I know students have problems with this. Okay, once you learn what you're doing, you don't have to do this one little step, but it's kind of nice until you're really comfortable and understand what's going on. So just be very clear in your mind that this is a function of x. That's your variable. This is a function of x. So let's go ahead and take the derivative. So derivative of x is 1. Derivative of y of x is just dy dx. See the difference? That was just 1. This is dy dx. Because this is the variable, that's the function. Excuse me. Derivative of x cubed is 3x squared. What's the derivative of this thing? Here you're going to have to use the chain rule. It's going to be 3 times y. I'm going to just not put all those x's in there each time now. 3y squared times the derivative of the inside. The derivative of the inside is dy dx. Okay, so 3y squared dy dx. Again, notice the difference between this and this. This is just the variable. This is the function. So they look the same, except basically you have that dy dx as a tail. Okay, what happens here? Use the product rule. Product rule says I take the derivative of the first times the second plus the first times the derivative of the second. What's the derivative of this? You bring the 4 down. I left room for a 4. 4 times this thing cubed. So 4y cubed times the derivative of the inside, dy dx. And I left just enough room. The derivative of 28 is 0. So now, even though we couldn't solve for y here, we can solve for dy dx here. That's the nice thing about this process. So let's, here's the way I like to do it. I first find everything that has a dy dx in it, right there. And then I can do this in just a couple steps again. So I'm going to write dy dx times the quantity 1 plus 3y squared plus 4x to the 4th y cubed all that is equal to, that was all the things with dy dx. Now I move all these other things to the other side. So it's going to be a minus 1 minus 3x squared and minus 4x cubed y to the 4th. And then same as I did before, the last step, you just divide through by this whole thing. And then you've got your derivative. So there's your dy dx. And now all we have to do is evaluate that at the point 1, 2, which for me is the hardest part, just making sure you have it right. X is 1, y is 2. So it's going to be 1 minus 3 is minus 4. This is going to be 16 times 4 is, let me just do it up above here. It's going to be minus 1 minus 3. This is going to be 16 times 4 is minus 64. So 64, 65, 66, 67, 68. If I'm doing that right, it's going to be negative 68. And on the bottom, it's going to be, this is, oh, I made a mistake here. This should have been a 4x squared y cubed. Y cubed. There we go. So this is 2 cubed is 8 times 4 is 32 plus 12, 32 and 12, and a 1. So that's what? 45. So there's your slope right there at this particular point. So similarly again, if you wanted the equation of the line, you go what? Y minus 2 is equal to negative 68 over 45 times x minus 1. And so there's kind of what you need to know about implicit differentiation. This is how it's used, and this would be a very typical kind of problem just to see how it can be used. Okay, that's it.